Hello, everybody, and welcome to this webinar. My name is Felix, and I'll be the host of ceremony today. And this webinar will be about creating an ergonomic assessment. So we want to go over all the steps of an ergonomic assessment. So from the recording to biomechanical analysis and a report. So tell you a little bit about this. For those of you who don't know Xsens, Xsens is a motion capture system developer, and we are organizing this webinar together with Ottobock, Anybody, and IMK. And what we want to discuss in this webinar that takes from 10:30 to 12 today, so 1.5 hours, we want to show you what we can do together. So we did a project together as well, named the Andy project, how to perform an ergonomic assessment step by step. So we want to start with an introduction by Ottobock, giving a view about the industrial exoskeleton and the need of motion capture to show the efficiency of the exoskeleton in an industrial setting. So once we have established that, Xsens will provide the information on how to process the recording data in order to get the best kinematic data, and from there on export it to Anybody, in which you can do your inverse dynamic study. So Pavel will tell you a little bit about that. And finally, IMK will describe how to interpret this provided data and how to perform an ergonomic assessment with it. So it's really a full ergonomic assessment from A to Z, all the steps that you might want to cover in your own situation. So this is the agenda for today. So a short introduction of the webinar. It's only a few minutes. So Ottobock is ready to start, I assume. So as I mentioned, from this task to data recording, every session takes 15 minutes. So Ottobock, then we have Xsens, Anybody, and IMK. At the end, there's a Q&A session. So I would like to ask you, if you have any questions, that's perfect. Just post them in the chat box or the question box in our GoToWebinar tool. At the end, we will all start our webcam and we will do the Q&A session. I will ask the questions to the presenters on behalf of you, on behalf of the audience. So if you have a question, please also mention for who it is addressed to. It might be that there are simply too many questions. In that case, we will make sure that the questions get addressed to the right person so they can contact you afterwards. And also, if you have any questions that pop in mind afterwards, feel free to shoot us a message. We will also send you an email later on with the recording of this webinar, that if you want to watch it again or you want to share it, feel free to do so. So to go a little bit over the speakers, I will pop them up again. So we will start with Jonas, and Jonas is the project and technical lead of the Global Research and Innovation for Ottobock. He's working for Ottobock now for 7 years and has been working on industrial exoskeletons, devices, and wearable motion capturing. So he has a lot of expertise and knowledge in the industrial exoskeletons, and also IMU, so the trackers that Xsens uses, data analysis for activity monitoring and ergonomics. So I'm sure he will be more than capable of telling you a really interesting side of the story on the side of Ottobock with regards to ergonomics. Then we go to Maria. Maria is a product specialist at Xsens. So the technical support, she works at the Xsens headquarters in Enschede, and she supports our customers in Europe, Middle East, and Africa in the field of rehab, sport science, ergonomics, and biomechanics. So she has a lot of knowledge about the field and the questions that customers typically have with regards to ergonomics. To come back to myself, actually, I didn't give a proper introduction there. I'm the business developer in EMEA for ergonomics. So if you have any more commercial related questions about the system, please don't hesitate to contact me. For Anybody, we have Pavel, a senior consultant at Anybody, working there for over 10 years already. Has done a lot of investigation and research in the biomechanical modeling, and he worked at the Andy project as an affiliated researcher. And finally, but not least, we have Lars for IMK. He's the manager of the ergonomic division at IMK in Germany, and he's an expert for ergonomic consulting in the industry and simulation methods. And in the Andy project, he's responsible for the creation of ergonomic models based on the Anybody simulation results. So a perfect mix if you look at the combination Ottobock, Xsens, Anybody, IMK. So without further ado, I would like to give the words to Jonas, who can tell you a lot more about Ottobock. And yeah, I hope you all enjoy this webinar that we are going to present to you.
Thank you, Felix, for your introduction. And thank you to the audience for joining this webinar. So yeah, as Felix already mentioned, Ottobock, we are a manufacturer since several years now already for industrial exoskeletons. And I would like to show you the motivation doing this ergonomic analysis and assessment with the tools that are here presented, and the perspective of the developers of these exoskeletons, and how these technologies can help to improve the development of these devices. So as you can see here, we have several products like the Paexo shoulder and the Paexo back. But maybe I will start with a few words about Ottobock. Probably you know Ottobock as market leader in exoprosthetics. So Ottobock was founded 100 years ago in Berlin, and Ottobock is a great supporter of the Paralympic Games, and therefore also very well known. But as I said, we used our experience in biomechanics to open up a completely new field some years ago, and this was the field of industrial exoskeletons. And so besides our traditional fields, we applied our knowledge from 100 years experience in biomechanics to the field of industrial exoskeletons. And the motivation to do that was that industrial partners asked us. They probably had a lot of problems with musculoskeletal disease. So as you can see, the shoulder and of course the back are affected by a lot of musculoskeletal disease, and this is a big cost factor for manufacturers, for example. And this is a still ongoing trend due to the demographic change, and therefore, we started the collaboration with industrial partners, and in 2012. So maybe a few words about industrial exoskeletons. As you see, the idea to support people with an external device or a wearable device is quite very old. So on the left side, you see a patent application more than 100 years ago, supporting, or at least the idea to support workers in agriculture. And but the evolution of this is quite hard. So we have now moved from passive exoskeletons more and more into active exoskeletons. But the idea that both exoskeletons have always in mind is the industrial exoskeletons should support workers performing demanding tasks. And the big advantage of these devices is they preserve the human in the production process. And this is quite very important, because the human is still has a high adaptability and agility in the production process, and is still needed in a lot of processes. So it preserves the human really in the production. And also because of that, there's only a limited amount of modifications needed on the workplace. And as I said, with the development of better biomechanical analysis, of better motion capturing systems, the field of industrial design is quite very dynamic over the last decade. So there's a lot of competitors and a lot of research going on in this field. So at Ottobock, we drive user-centered design and implementation process for industrial exoskeletons, which we established with our research partners here in the Andy project, but also with our business unit, of course, who are doing the product development. And this is quite very important to have this user and stakeholder, this centered design in each development phase, because you can imagine that when you are in the production, there's quite also a big field of different stakeholders that have influence on this development. It's of course the worker should be the center of all of these developments, but still there is like working safety, occupational health that are also an important role in the development and of industrial exoskeletons. But in this user-centered design circle, we say we will focus today on two aspects, because we want to focus on the technology we use with biomechanical analysis, like the antibody simulation software, and of course the motion capturing of Xsens. And we see there are two motivations to do this in this design phases. And this is in the early phase of the beginning, when we do the analysis of the workplace, because we want to develop exoskeletons that support the workers in the situation when they need the support. So when there is an ergonomic risk, and not in situation when they don't need it. This is also very important to have then the acceptance of the device later in the implementation and application of in the work environment. So, and in this case, we're using these technologies of biomechanical analysis in the early phase to define the requirements. What should the device give for a support to different situations? How can we give the right joint moments and so on and so on. This is quite very important for defining the requirements and doing the prototyping. After the prototyping, so when we transfer the prototype to the product development, we do a lot of evaluations still in the laboratory, but also in the field. And there we see a second important point to use biomechanical analysis and to record data in the field, because then we want to show the efficacy of our device, and of course having also the subjective feedback of the users and the workers. And for us, this is quite very important to highlight the biomechanical efficacy by objective results. So as you know, we are a medical device manufacturer. Even these devices here, industrial exoskeletons, are not medical devices, but we have the philosophy. So we want to have the same approach like we use for our medical devices, and therefore we try to use also the latest technology for this. And therefore we develop laboratory and field tests using especially IMU sensor technology, because we have there the best flexibility. And the simulation is, from our point of view, very important, because we cannot measure the joint forces so within the body. And this is quite very important to show really what is the reaction of the body and the interfaces for the device. And therefore we think there's only one good way, and this is having a really good musculoskeletal simulation to show this. And of course, still we do also long-term laboratory and field tests because we all know musculoskeletal disease is a long-term issue, and therefore we need to highlight this over a long time and not only on a short window. So we think about a frame of over certain years to observe these developments. And what is so challenging with this? There is not only this one overhead task. And therefore the need of doing this analysis is even more important, because what we already know from the application of our Paexo shoulder is that it is suitable for a high variety of overhead tasks. So we have more than 500 customers in different industries. So in the automotive, transportation, aviation, shipyard, or even in the construction industry, which is quite even more challenging because of the different tasks you have there than compared to the automotive. And that's why we think it's very important to do this analysis to do not harm people on long term with these devices. And so to sum up this, there is not this one overhead task, and this makes it even more important to do this kind of analysis to understand better the ergonomic problems. And always remember, we want to avoid musculoskeletal disease on long term, and therefore we need devices that are carefully developed on the latest technology which is available. So thank you very much. I would like then to show you the references and hand over to Maria.
Hello everyone. I hope you're hearing me. I would like to thank Jonas by the presentation, and I would like to follow up his presentation by explaining you how we can go from the recorded data with our sensors to having this estimate all the different kinematic parameters, and emphasizing how Xsens can record anywhere in any type of environment that you are. So Xsens has been working with IMU technology for 20 years now. And this is one of the reasons why we have so good motion capture, and because of the knowledge that we have been gathering throughout these years. So Xsens started as a startup in the University of Twente in the Netherlands, and until now have been expanding. So we have already offices in the US and in Asia, and a lot of distributors around the world. So as a normal workflow with motion capture and with IMU sensors, we start by placing the sensors in certain segments, and then the sensors send data to a receiver that is connected to your computer. And at that moment, at the software level, we assign each sensor to a certain segment. We change the body dimensions of our avatar to fit the body dimensions of the participant, and we calibrate the system. And after calibration, the engine of our software and the very sophisticated algorithms can cope and estimate accurately all the kinematic parameters of the body, and you can have a real replication of the task that you are doing. So in terms of the hardware, Xsens has two main hardwares. So we have the link system and the Windows system. The link system has all the sensors with wires between each other, and they communicate via Wi-Fi. And the Windows system has all the wireless sensors. So each sensor communicates individually to the station. You can see that they change a bit of the battery, but you can record up to 7 or 11 hours with our motion capture systems. You can be around 20 to even 100 meters from the station. And both systems have a sampling rate of 1000 Hertz internally, but then we use a strap-down integration to send the data with a lower frequency but with the same quality. So each of our sensors has three main components. So we have accelerometer, which measures linear acceleration, and therefore points to gravity. Then we have a magnetometer, which points for the magnetic north. So we have a second axis. And then we have a gyroscope, which measures angular velocity within this frame. With these three sensing elements, we are able to measure the orientation in space of each of our sensors. And if we combine the information of all our sensors throughout the sensor fusion engine, we are able to animate our avatar in a very realistic way. So I would like to guide you now about the different steps that our data pass through by showing you three different videos. So you can see that if we just apply the sensors in the segments and we don't apply any constraints, we have the orientation of the segments being well estimated, but then they are just floating around. So what we need to do is to apply a biomechanical model and constraints to each body segment, and then scale and calibrate our model. In this case, you can see that the movement was well recorded, but there was a drift in position. And this is a phenomenon resulting from the IMU technology, since we need to integrate velocity to obtain position, and therefore we have accumulative errors. However, Xsens has been the past years developing a lot of algorithms that cope with these errors. So we have magnetic immunity since 2018. We have multiple contact points detection, compensations for skin artifacts. And I'd like to guide you further a bit into these specifics that make Xsens so good and with accurate data. So in terms of magnetic immunity, it does not depend on the hardware itself, but is a feature from the software side, which means that you can record anywhere you are. So you can be inside a car, you can be in a manufacturer as Ottobock represented, so you can be working on cars, you can be even on a harbor. There is no problem about the environment that you are because all the settings are made at the software level. Also, multiple contact points detection. So we are able to not only detect contact points at the feet to be able to have walking recordings, but we can also detect contact points at the hands. As you can see here, it was a recording from climbing, so we can see where the hands were placed and where the feet are placed. But also recordings, for example, for push-ups, where the feet and the hands are at the same level. And finally, the height tracking. So without any external cameras, we are able to detect the height tracking. So in this case, you can see in the ladder, we clearly on the right side, you have the graph, and you can clearly see that there is the steps in height that the participant is doing while climbing the ladder. So which type of data do you actually get with Xsens? So we have 17 sensors. So each sensor has orientation, acceleration, and magnetic field. And then our avatar has 23 segments. And each segment is connected to a 3D degrees of freedom joint. So you have 22 joints. So for each segment, you have position in space, orientation, velocity, angular and linear velocity, acceleration, and bony landmarks, which are estimated based on the body dimensions that you inserted to scale your avatar. And then at the joints, we have all joints are 3D with 3 degrees of freedom. So you have adduction, abduction, internal external rotation, or flexion and extension. So, and then we also have another estimation of joint angles, which can be very helpful, for example, in ergonomic analysis, which are the inclination, for example, of the pelvis with respect to the horizontal plane. So you can see the inclination of your trunk in several tasks. And finally, we also have the center of mass, the position, velocity, and acceleration. So in our software, you can have real-time graphs. So you can see immediately what the tasks they are doing. You can have an automatic processing. So it means that you don't need to really look into the data very closely. The processing that needs to be done is just by clicking a button. And you can also do it throughout the night. We also can stream the data real time to other third-party softwares. So all the data that you see and I presented to you before, you can stream it to other softwares to do further analysis and synchronize with other party devices. So you can synchronize with gloves, you can synchronize with EMG, force plates to get different data. So finalizing my presentation, we can export also the data, so you can record a file and export it in formats to import into different programs. BVH is one of the formats that anybody will use to import our data, but we also have C3D, Excel, so we have the columns of all our variables, and XML file, which is our MVNX file, which you can upload in also multiple programs. Or, as I said before, you can also stream the data into some biomechanical tools, programming softwares, or ergonomic analysis softwares. And with this, I would like to give the floor to Pavel to go further with the inverse dynamics study.
Thank you very much, Maria. So I will continue with the anybody part. So I will also briefly introduce my company. I'll introduce our products, and then we will switch to inverse dynamics and how we import kinematic data from Xsens acquisitions into anybody. And we'll talk a little bit about how we use external forces and how we can actually predict them. And we will then switch to a use case of simulating a workplace scenario with and without exoskeleton, and of course using Xsens data. And then I will conclude. So first of all, my company is called Anybody Technology, and we are based in Denmark, in Aalborg. And our main product is the Anybody modeling system, but it typically comes with the Anybody managed model repository, which means that you can already start working with a lot of different models that were created for you. And one of the models is actually a processing model for Xsens, for example. And we also do training, we do support, and we do consultancy if someone is interested. And we also have an associated research group in Aalborg University, very close to us, so we are up to date with the state of the art of the science in musculoskeletal model. And we also have a network of resellers all over the world. So our applications are basically wherever the human does some action. For example, we do some application in sports, in orthopedics and medicine, of course. There is also a lot of research happening in the university, and anybody is used in the automotive world as well for ergonomics of the cars and other things, in aerospace area as well, and of course exoskeletons, as it will be presented today, and ergonomics of the products and consumer products and so on. So the Anybody modeling system is a system to model human as a mechanical system. So we start with the human body model, which is a part of the Anybody managed model repository. So I will refer to that as MMR. And what we do with this, we subject this human model to some motion, and we apply external forces that we know about. For example, the force plate data that is recorded in the lab. And after this, we connect it with the environment, such as an exoskeleton. And once everything is assembled, we perform an analysis of the constructed problem. And this approach is called inverse dynamics, when we go from motion to the internal forces. And in order to find the internal forces, we need to solve a muscle recruitment problem, because there are too many muscles in our body, and basically we need to optimize the way the muscles work. And this is very similar to how a central nervous system works. So in a way, we try to mimic the central nervous system to distribute the loads all over the body. And once the problem is constructed, we basically get a simulation that shows you the individual muscle forces, joint reaction forces, and much more, of course. And eventually this can be used, as Jonas mentioned, in some sort of design loop during the prototype phase. And of course, anybody can be used in that scenario. So as I said, the first thing that we use in anybody is we define the motion. And there are different ways to add motion to the human body, but the easiest, of course, is always to just get a measured motion if this is possible. And we have a very nice interface to Xsens data through the BVH files. So inside of the anybody managed model repository, we have a dedicated processing model that comes together with the anybody modeling system. So you can start and basically start working with it right away. The model scales automatically the size of the human to the stick figure, to the avatar that Xsens outputs. And after this, what happens is that we try to convert the motion of the Xsens avatar into the anybody motion. And the reason why we need to do that, because the joint angles are not exactly the same as the full body model, because anybody model is very detailed. We have a lot of small segments, such as clavicle, scapula, and so on. And these parts are, of course, limited, like in Xsens output. So we do an optimization where we convert the data that is coming from Xsens into anybody. And we do that by placing markers on each segment that is available in Xsens, and we optimize the motion, the human to move according to these markers. So we call this the virtual marker method. And that basically gives a motion like you see on the picture. So we have a human and we have the stick figure overlaid. And yes, so this is the process. Because Xsens is capable to record the motion outdoors and in, let's say, industrial settings, typically it is very difficult to install force plates, and let's say there are never force plates in an industrial setting. So another good feature of anybody is that we are capable of predicting the ground reaction forces and other sorts of interaction forces with the environment. And I will demonstrate it here. So we can generally predict any friction-based contact force, whether these are reaction forces or interaction forces with the environment. As you can see here on the leg press machine, so there is interaction with the back, with the feet, and here the person is polishing something, and there is interaction forces with the environment as well. Or you can also look at this as interaction forces with the exoskeletons, but yeah, there are some limitations, of course, as well. And the general question is how valid is the prediction of the ground reaction forces? And we were partners with Xsens in another study called, in another European project called NEMO, where they did an analysis of the prediction, and they measured ground reaction forces in an experiment, and they compared the values, and it turned out to be quite good. And this was previously presented in another webinar as well. So all of these methods, they are applicable to different scenarios, of course, but we are talking about the ergonomic assessments of a workplace. So here in the Andy project, we did a special use case where we tried to simulate a lab study in which an exoskeleton was assessed for its effectiveness and performance. During this lab study, the motion was captured as well, and external forces were also measured. And the goal of this study was to output some biomechanical information for each participant for further in-depth ergonomics assessment that will be presented by our partners from IMK. And we also want to understand individual muscle forces and joint loads to understand how efficiently the exoskeleton, what parts of the body it unloads, what muscle it unloads, and maybe some muscles are loaded instead of unloading. So we would like to look at all of that. So as a data source for our simulation, we used a data set that was collected in the Andy project as well by our partners, and it was a very great data set with a lot of data collected. So the whole body kinematics was captured with Xsens inertial motion capture suite, and there were a lot of other things measured as well. But for our purpose, what is relevant is the position of the drill, sensorized shoes that measure reaction forces from the ground, and of course the motion of the body. So we use this information in our simulation. The whole experiment consisted of 12 subjects performing some sort of task, and this task was to simulate some overhead work for 2 scenarios, where in one scenario the exoskeleton was used and another scenario was when the exoskeleton wasn't used. And each of those scenarios was subdivided into 5 sets of sequential motions, and each set consisted of 24 motions. And as an output of the study, we of course wanted to output the information about the muscle activations and all kinds of muscles, spinal muscles, shoulder joint reaction forces, and of course the loads on the spine, for example. So we try to look at different components of the body. So for this purpose, we had to create the PyExo shoulder model. Unfortunately, the motion was not recorded for the exoskeleton itself, so we basically allowed any body modeling system to predict the motion. And for that, we needed to construct a very accurate model of the exoskeleton. So we created the exoskeleton model in anybody according to the specifications that were provided by Ottobock. They provided us the CAD files, the dimensions, the support torque functions, and so on, and guidelines how to position it on the subject. And we of course used all the kinematic information according to the specification as well. So we allowed the exoskeleton to rotate on the hip, and the belt was rigidly fixed on the pelvis of the human. So the shoulder had a shoulder joint, which was a revolute joint, and so on. We also allowed the exoskeleton to slide along the arm, along the length of the arm, and the load transfer was also according to the specifications of the exoskeleton. There was one additional thing that we did. We allowed the exoskeleton cuff to rotate around the axis of the arm as well. So, and that was done using something that we call soft constraints. Once we had everything set up, once we had the model of the exoskeleton, we had to process all the trials, and it was actually quite a lot of different trials to process. So we had 12 subjects, 2 scenarios, 5 sets of 24 motions. So in total, these were nearly 3,000 trials that we had to process, and that was of course not possible to do manually. So we tried to do this in using a tool that anybody has, was developed by one of my colleagues. That's called AnyPy tools. It allows to do a batch processing of anybody models, and it allows to communicate with the console version of anybody modeling system. and it's a Python library, and it uses a special macro language. And basically, having all these tools allowed us to process everything in parallel, so we did it much faster. So I think the total processing time of this whole large data set is actually about 4 hours at the moment. And as a result, basically, we got information about each joint, how each joint is being loaded, and yeah, so we could do the final analysis. I'm not going to talk about the results now because I will give an opportunity to our partners from IMK because they are ergonomics experts, so they carried out the analysis of everything here. But I could also say that what can be done in anybody is that we can look not just at each muscle as anatomical muscle, but we could also look at individual muscle branches, for example. So we could see how muscle forces migrate for some motion. So, for example, we could see how a muscle moves from, let's say, from inner side of the muscle to the outer side. And you can get quite a lot of useful information. So I think I would like to summarize that Any-Body Modeling System is a useful tool, and we try to develop it even more in this direction to be even more useful, to do biomechanical analysis, and whether it is applied to ergonomic scenarios or to other scenarios. We have a rather easy import of the data from Xsens and, of course, other motion capture system. And the human body model that we use is very detailed, so it contains most of the muscle, so it's very accurate. We also have options to predict interaction forces with the environment, which is one of the key features in Any-Body. And we also have a muscle recruitment strategy that supports that, because we need to handle closed loops scenarios, and this is very important for the exoskeletons, because once you put an exoskeleton like Piexo shoulder exoskeleton, you create a closed loop, and Any-Body Modeling System, due to specifics of the muscle recruitment strategy, is capable of doing that. And of course, we have a very nice batch processing utility for handling large data sets like the one that we are talking about right now. I would like to thank you for attention, and I will give the word to Lars now.
Yeah, hello everyone. From my side, my name is Lars Fritzsche. I'm responsible for our ergonomics division at IMK. And well, I'm going to talk about assessing the results that we get from biomechanical simulations in terms of ergonomics. So this is my agenda for today. First, a few words about IMK, our simulation framework. And then I go into the results that Pavel already started to talk about. IMK is located in Germany, in Chemnitz and Stuttgart, and we have an ergonomics division of about 15 people working in the virtual ergonomics field, risk assessment, product and process design, and consulting and training. So we work a lot of, the majority of our projects are in the industry. We do about 10% of research and development. At IMK, we have also, during the last 10 years, developed our own software for process simulation in the virtual digital factory. It's called EMA. And you can see an example here. Based on the simulation, you can basically do a time analysis based on the MTM standard. You can do an ergonomic analysis based on the EWS standard. Can do some sequence planning, the path planning and layout planning, and also, of course, some documentation and reporting. So EMA has a connection to Xsens already. So basically, we can use Xsens captured data and transfer them into our EMA model. we don't have a live streaming yet, but we can use BBH files and stuff like that. In the EMA simulation, we can then combine Xsens data with basically our standard work tasks and add some tasks to the captured data. And based on that, we can do a semi-automatic ergonomic assessment of the captured motions. Here are some things that you can get out of such an ergonomic and productivity assessment. So of course you get automatically information about body postures, durations for a part of the EAWS assessment. Of course, you can get information about body parts, spine, and so on. You can still analyze the walk path and also to some extent, we can look at the time analysis already. We also have established a connection to the Anybody model. Well, this is, whereas Xsens is already working quite stable and well, this is still a prototype because the EMA model and the Anybody model is quite different in terms of details, but there are ways to transfer data from EMA to Anybody and also back to EMA for maybe optimizing the movements and also the biomechanics, kinematics of the EMA simulation itself. This is important because this is all part of our general simulation framework in connection to this topic today. So as an input, we can use motion capturing, as you have seen already, and we can also use this in combination with EMA simulation. And of course, in Anybody, you also have the possibility to use the Anybody drivers. So it's a script-based modeling that is that comes with the Anybody modeling system. It's of course very hard to learn and understand. That's why we're trying to create other input channels as well, so we can concentrate on the processing of the data in Anybody. So as Pavel has mentioned already, of course, we can do manual analysis of single movements and participants for creating a model, but then we have to select a set of parameters that we want to analyze, and then you can maybe do a script-based analysis of a large data set as well. And then, of course, we get the output, and the output from Anybody is is very diverse. So you can get a lot of parameters and a lot of results about muscle activation, joint reaction forces and moments, even some metabolic information and other kinematic analysis. We also try to work on an ergonomic score, but this is not really finished yet. But I think one of the main strengths of the Anybody model, from my point of view, compared to standard ergonomic models and methods, is that you can you can look at very detailed effects in the body, individual effects. You can, differentiate between left and right side. And of course, you can also, it also allows you to not only look at maybe intended main effects of some ergonomic measure, like an exoskeleton, but also other measures. You can also look at negative side effects if there's any different distribution of loads in a different part of the body due to that measure. And this is something very important for the topic of exoskeletons, of course. So let's take a look at the detailed results of our study here. And Pavel already showed the setup, and this is again, just as a reminder that you can see that we can transfer basically the data that was captured in the lab to our EMA model and to the Anybody model. You could even use EMA for optimizing some of them, for adding some tasks if you would like. In this case, we didn't have to do that, so everything was captured and directly then imported into Anybody. Yeah, here I hope that you can see the videos quite well. Now, what parameters did we look at? Of course, we looked at the, because this was, we used the Pixo shoulder exoskeleton as a use case, and of course we look first at the intended main effects. So the shoulder muscles, how does the exoskeleton affect the shoulder muscle activity, and also the joint reaction forces in the shoulder. You can see here the muscles that we chose for our analysis. And as Pavel already showed, you get this kind of result from anybody. This is one way of looking at it. But the problem is, I guess, many people, especially in the industry and in working in the field of ergonomics, are not specifically experts in biomechanics, and they cannot really differentiate between all these muscles and all the muscle parts. So you have to summarize this a little bit. So one thing that you can do is looking at the curves of the parameter in this task. In this case, the deltoid and the anterior and deltoid lateral. So that's the muscle in the shoulder. And this is just an example from one participant, one task cycle. That shows that basically the activation with exoskeleton is quite much lower than the activation if you without exoskeleton. I see a laser pointer now on the screen. This is not my laser pointer. I don't know. Am I moving that? Because I cannot do anything. So basically, this you can see these variables, and now the question is how to do an interpretation. So maybe as a first idea, we thought about the the classical permanent endurance limit that is used in ergonomics and also sports engineering for quite some years, which is about 15% of total muscle force. You can see that here, it shows, looking at these curves, it shows already that gives you an idea that maybe using the exoskeleton with the blue line, you can maybe stay below that that limit, in the long run. Another way looking at the results is drawing all the results that you get in a box plot like this. So this is actually based now on all the data from all participants in both conditions, with and without exoskeleton. And you can see on the on the left, it's both box plots basically are from the same muscle, the deltoid anterior in this case, just as an example. And you see there's a difference, of course, between the left hand and the right hand, or the left shoulder and the right shoulder. Because in the right hand, the participant is basically holding a tool. The tool weight was about 0.6 kilogram. And of course, with this hand, he's also doing some dynamic movements. And what you can see on this slide is basically that, it's very plausible that on the left side, you have quite a low activation. And the activation in the deltoid is even lower using the exoskeleton. But the difference between no exoskeleton and with exoskeleton is not that big. If you look at the right side of this slide, and also the results of the right deltoid, then you can see that the muscle activity without exoskeleton is now much higher because he's holding that tool. And with using the exoskeleton, it's still very low. So this is really an effect of the exoskeleton that is taking, compensating a lot of this load due to the tool usage on the right hand and right shoulder. And you can see the distribution of all values in the histogram on the bottom. Well, how does it look like for muscles with no big difference? Just as an example here, the erector spinae. So this is in the lumbar spine in the back, or not lumbar spine, but in the back spine. And you can see here, there's no big differences between left and right side, and also not a big difference between exo and non-exo condition. Okay, so another way of looking at that, we looked at a statistical analysis of the mean and values, standard deviation, and the maximum values that you can find in these in this data. And what you can see is that here on this slide is that the mean activation for the deltoid anterior was about 20%, lateral 29%, infraspinatus 37%. So especially the deltoid muscles could be reduced a lot by using the exoskeleton. We are still looking at the exact numbers, so this is preliminary because there's also a way to adjust the force that the exoskeleton is providing. Also in the antibody model, we're looking at that. But in general, you can see a strong reduction in these kind of muscles, but in other muscles here below, you don't see this kind of effect. Either there are no significant changes in the muscle activation, or the baseline is very low. So these muscles are not really relevant. Well, then you can look at the joint forces as well. And in this case, the joint reaction forces for the shoulder joint, specifically the glenohumeral joint, and also in the spine. With the same methodology, you can look at them looking at the mean forces that you can see here, and with and without exoskeleton. Without exoskeleton is much higher again than with the exoskeleton. So here you can see reductions of 80%, 57% in the glenohumeral joint, different directions. And here for the lumbar spine, and on the other side, you don't see any significant changes. And this is also, of course, intended. So we don't want to see changes in the lumbar spine, because this would mean that the load is increased due to the usage of the exoskeleton, or it's somehow changed due to the usage of the exoskeleton. So, and you can see that again, also with an example from one participant, also in the curves in the lumbar spine in this case. Well, of course, there's not much time today to go into each detail, but you have seen some of these results and how we interpret them. For us, this was the first way of looking very closely at what we can do with anybody modeling system, and how we can supplement our standard ergonomic assessment tools with this kind of biomechanical detailed approach. So I think our conclusion is that the simulation allows to evaluate exoskeleton prototypes and also products regarding their biomechanical and physiological effectiveness. We can test design variants and functional design specifications without any risk and with relatively low effort before building physical prototypes. Of course, this is a general advantage of doing simulations. And you can eventually gain insights on how to optimize the design of exoskeletons to better fit a specific use case and or a specific user population. Now, in this case, we didn't, use case and the population was somehow given, but of course, then you can change the anthropometrics of the model. You can look at small people, at tall people. You can change the weight of the people and see how this affects the effectiveness of an exoskeleton or other ergonomic measures. So that's why personally the conclusion is that the simulation with anybody, they go beyond standard ergonomic assessment methods like EAWS, ruler, etc., because they look inside the human body for main effects and side effects. This is something these observational methods cannot do. They were not designed for doing that. And simulation studies should, of course, also be used proactively in the design phase and as a supplement of lab and field studies to investigate existing products. So we don't think that you should only use simulation studies for doing such an analysis of the effectiveness of exoskeletons or other tools. But I think since there's certain extra insights that you can only get with the simulation, each test trial that is evaluating such a technology should include a lab study, should include field studies with users, but also should include such a simulation. That's my part for today. Thank you for listening.